Welcome to the second talk of the evening. The second talk of the evening will be given by Dr. Narayanan Unny on global local scalable explanations using a linear model tree. Dr. Narayanan Unny has been a machine learning researcher for more than a decade, and he did his PhD in Bayesian learning from University of Edinburgh. He then started his work in industrial research in Xerox Research Center, where he had contributed to the use of machine learning in intelligent transportation systems, including some of the transportation systems in India. This research included use of machine learning to aid robust and dynamic scheduling of public transport. He currently leads the research team on machine learning in AI labs within American Express, and is currently actively researching different aspects of ethical AI and differential privacy. It's a pleasure to have Dr. Narayanan Unny present talk on global local scalable explanations. And over to you, Narayan.
Thank you, Harish, and thanks to all the organizers who have organized a conference on this very relevant topic. So, like Harish introduced, I am currently leading the machine learning and optimization group within MX AI Labs. And within AI Labs, we look at different problems related to the business around MX, which is mainly credit cards and loans and so on. So in particular, we look at the analytics behind it. And just to give you an introduction to explainable AI within the financial world. So this has been around for a lot of, years in the financial world, wherein by law, if you deny credit to an individual, you are supposed to explain why it happened, right? And so with the advent of new ways of learning with more complicated models, explanation has become a very required element of machine learning. So I would be giving a talk more from a practitioner's standpoint, and my collaborators on this has been Aditya and Alireza from MX as well. So just to set the context, and probably by now everyone knows about it, that what we call as an explainable model is a model that is interpretable by a human being in terms of telling something about a particular complex model. So it could be an inherently interpretable model, or it could be a model built on top of a complex model to explain the complex model. And again, the objective here is to try and explain why a particular complex model, be it a neural network or a GBM model, why does it perform, why did it predict something the way it did, right? So that is a basic objective. Now, there are different forms of explainability for a complex model. It could be presented as rules, or it could be in terms of feature attributions. So if you look at anchors, it provides rules to tell you why a particular decision was made. And if you look at things like SHAP or line, it gives you feature attributions which are ranked according to the importances of the features that were involved in the prediction. Okay. And that could be also another way of classifying explanations could be on the granularity of these explanations. So you could have global explanations, which kind of provides a summary of the complex model, an easy to understand summary at that. Whereas a local explanation could be an explanation about a particular test point and why did the test point predict the way it predicted. So why was someone refused a credit or things like that. And each of these serves different purposes, right? And that is uh, very important to realize that a global model, a global explanation serves a particular purpose, whereas local explanation serves another purpose, right? And sometimes you need to choose between these two to understand to get a better understanding of what these predictions mean, right? For instance, if you are interested in the relative importance of features at a global level, you would use that. Or you might want to use explainability to understand model drift. Why did a model's performance deteriorate over time? Whereas in a local setting, you might want to compare two different people who got two different predictions. So you might want to understand what is different between them. And so you would want to have more localized explanation. So in essence, one of the main takeaways that I would want to emphasize in this talk is more around as a practitioner of machine learning, you must be very careful about how you choose the explanations, what form you choose, what is the granularity you choose, and so on. And again, there is this famous paper by Zachary Lipton about methods of interpretability. So deriving out of that, you would uh, need to kind of choose these explanations or methods of explainability based on your particular use case or particular context in which you are using. Like, for instance, you could combine a local feature attribution to come up with feature importances. So telling someone why credit was denied. Or it could be a local rule-based explanation, which is useful to understand the localized behavior of the complex model. And you could run what-if scenarios and counterfactuals and so on. Whereas if you have a global rule-based model, it could be very useful to understand the subpopulation behavior. How is the complex model treating different subpopulations in the group, right? And again, global feature attributions could be useful to understand the model at a high level. Probably you have a question that if I add a new feature to my model, how important that feature is to the model and how different are these two models going to be, right? So just to give you an illustration of why this is important, I would give you a negative example of why it is so. So consider two simple models. So for this exercise, we will assume that model 1 and model 2 are the ground truth or as well as the complex target model that we want to explain. So the only difference between model 1 and model 2 is kind of a mirror symmetry between the regions of space. So for positive x1, the y has a particular linear form. For negative x1, y has another linear form. And these two are flipped between model 1 and model 2. And what you can see is that the feature x1 is important whenever x1 is positive, x2 is important when x1 is negative, and vice versa, right? So let's choose a global feature attribution explanation for this. And very frequently, what people would do is that you would come up with local explanations for individual test points and then take an average to understand the global feature importances. Of course, if you had to do this, you would find that the importances of x1 and x2 at a global level are the same, and which is true, right? So you have the same feature importances. But if you want to understand at a more granularity why model 1 is different from model 2, you would need a different form of explanation as well as different granularity. So if you were to use instead a rule-based explanation, you would probably be able to find that indeed model 1 and model 2 are different with different feature importances, right? So this toy example kind of illustrates the need for combining different forms of explanations with different granularity based on what is the need for that particular uh, problem. So some of the limitations that we found with current explainability methods is that they are either purely global or purely local, and they either produce rules or feature attributions. And one important thing is they don't scale to large data and complex decisions. Right? So what our approach has been, and I will come to that in a short while, is to build a simple surrogate model. And this is something that has been in vogue for a long time. So the idea is quite simple. So you have this complex model. Now what you want to do is to want to explain this complex model. So what you could do is probably build a surrogate model that is quite simple, and so it is interpretable, but at the same time it can mimic the complex model as best as possible, right? So in our case, this particular surrogate model is what we call as a linear model tree. So the linear model tree is your vanilla decision tree with some modifications. The modifications being that instead of having a plain split, we basically split based on linear fits at each of the nodes. So basically what you do is at each node, whenever you want to split, you try to fit the data points in your children with linear fits, find out which gives you the best, which feature gives you the best split, and so on, so that at the end you will have a decision tree with linear fits in the leaf nodes. So what it gives you is basically, whenever you talk of the explanation, it gives you a context, right? So it combines the rule part with the feature attributions. So the rule part is basically the decision tree, which tells you something about the region of space. So it will tell you what the complex model is trying to do, how does it behave in different regions of the input space. And when you reach the leaf node, it will also, with the help of these linear fits, it can also tell you what are the important features that that model that particular subpopulation, the subpopulation for that particular leaf node, right? So using this principle, you can both build a global model, as we see here, or you could also build a local model. For a global model, you basically use your training data itself to fit this linear model tree. Whereas for a local model where you might not have the training data, you might or might not. If you have, you could utilize that. But if you don't have, you could basically sample using some standard sampling methods. In our case, we used CT GAN to sample the neighborhood around the test data point, build a similar linear model tree, and basically use that for your explanation. So, so relating this back to my original message that you need both global and local levels of explanation. So what it now it provides you is the flexibility to understand the complex model at a granular level, as granular as you would like to, right? So you could If you are happy with a shallow tree, you would have a shallow tree, but if you want to dig deep, you would expand the tree and make it more and more local. Right? So that's the simple idea behind LMP. So just to give you a demo of how it looks like and what it learns. So there was a challenge a couple of years back from FICO. So FICO is the credit scoring company. So they released data which consists of basically some features of a particular individual, and the label is basically if that individual is risky to default on the loan or not, right? And the challenge basically was to come up with explainability tools that can explain the decisions made by their complex model. So just to give you an illustration of how it looks like. So this is, so it has a number of features. So things like external risk estimate, which is a estimate by an external agency on the risk of the individual. Then you have the months since oldest trade open, and some important things like the months since most recent delinquency and so on. And what is interesting is one way to test sanity is also uh, it gives you the monotonicity of this feature in explaining the risk, right? So if you look at this feature, for instance, the month since most recent delinquent, as this increases, so the number of months increases since you last were delinquent, the risk decreases, right? So basically that is what is indicated. So if you were to use this, and if you were to build a really shallow LMT tree, then you get something like this. And what it helps you do is basically these variables basically creates these subpopulations, and using those subpopulations, you can take up those subpopulations and understand, I mean, you can deep dive into these subpopulations to understand why something is behaving the way it is behaving. And this is especially useful in cases where you have the data drifting across time and you want to understand why the model is behaving the way it is behaving, and things like that, right? And so this is the tree, and each of these leaf nodes in turn will have its own feature attributions. And you can see the kind of a clustering effect that you get. So in the top node, it's all green, and green means that it has a monotonically decreasing relation with the risk. Whereas if you look at uh, the other node, it is kind of opposite. You have lots of reds, so which means that it's influencing in the other side, and it makes sense because these basically the clustering it has done is in such a way that individuals who are highly risky are grouped together, and the low risk individuals are grouped in the other cluster. So the feature importances will also differ accordingly, right? So this was LMT at a global level. So returning back. So this is how you can get, and again, going into the leaf nodes, you can basically understand what is happening. You can run counterfactual what if scenarios to understand if a particular feature of a particular person changes, what will happen to the risk of that person, and so on. So this is kind of a summary of what exists today, comparing LMT with other open source tools out there. So LMT provides both feature attributions and rules. It provides global as well as local kind of explanations and so on. Right? So how do we evaluate explanation? And again, many of the speakers before me have kind of touched upon this topic, and it's a very tricky subject because it involves human subjectivity. So you don't know what the best explanation is. But nonetheless, you can at least measure how close your explanation is to what the complex model is predicting, and which we call as fidelity. So you compare the predictions made by the complex model and the predictions that your explanation method gives you. And if they match well, you say that the fidelity is high. If they don't match, the fidelity is low, right? And as you can see, the LMT provides good fidelity numbers, and more focusing on the global part of LMT, it gives quite a good fidelity compared to the global counterparts of line and SHAP. Of course, we cannot have 100% fidelity. If that were possible, then I would just replace the complex model with my simple surrogate model. So I wouldn't need such a complex model. And what is also quite interesting are the run times here. So since it's a fairly simple algorithm to construct a surrogate decision tree, it runs fast, and so you have orders of magnitude better performance compared to some of the other techniques. And another dimension to compare this is along the rules that are produced by LMTE. So you can understand how good the rules are by comparing the coverage that it produces and the precision it produces. For instance, anchors is built to produce precise rules, but then the problem is that you would need many rules to cover your entire uh, space, right? So again, lore is kind of again explainability method based on decision tree, but it uses genetic algorithm to build a tree. So you see that LMT, if you look at the F scores, LMT clearly dominates, and it kinds of balances coverage with precision. And again, it's tunable. You can look at very local, very specific rules, or you could look at very generic rules as appropriate for the problem at hand. Okay, so that's more or less about it. So just want to end the talk with the message that whenever we look at explainability methods, whenever we want to use explainability methods to explain complex models, we need to take care of what is the form of explanation, what are the granularity of explanations that we require that would be suitable for a particular problem at hand. Right? Thank you all. Happy to have any questions.
Hello, thanks, Narasu. It's a great talk. So I have one question. There are a couple of questions in the chat, but before we go there, I have one question. So the LMT model that you train, does it use the complex model in any way, or does it directly use the data?
It, yeah, like other surrogate methods, it basically queries the complex model for predictions. And based on that, it builds the decision tree. So it basically trains the LMT or the decision tree on this particular data that is the input and the output from the complex model.
Oh. So, but for example, if the complex model has, let's say, 100% accuracy, then it is equivalent to training on the training data. Is that correct?
Yes, but yeah.
Do you train the LMTE on just the data samples, or do you go out of the data also? For example, you can, in principle, let's say you have a CIFAR10 classifier, let's say, and you are trying to, you don't need to give CIFAR10 images. You can just give random noise images, because your neural network can classify in random noise images also. Does the surrogate method also use such data, or does it just use the training data itself?
It depends. In many cases, in realistic cases, you might not be the person who built the model in the original place, right? So you might not have access to the training data. So you might have to build your own data. In which case, yeah, it will be outside the data that the neural network model had seen. Otherwise, if you do have the training data, you could utilize that.
Yeah, interesting. So how is LMT, let's say, different from, let's say, a simple regression tree?
It is different in the sense that the linear fits are happen. So if you take a leaf, instead of the leaf having a constant prediction, you would have a linear fit on the leaf. So it is kind of it kind of is more generalizable when compared to a simple regression tree.
So that means that the linear function at the leaf node kind of corresponds to the local explanation, and the tree corresponds to the global explanation. Is that the way to interpret?
Yeah, yeah. Local explanations for that particular subpopulation that corresponds to that leaf. But you could also have LMT for just one point, right? So you could sample around the neighborhood of that particular point and build the whole LMT. And that would correspond to the LMT explanation for a single point, just like Lime does it.
Mm-hmm. So, but that means that you can always achieve 100% fidelity, right? So if it's a tree, if by going deep enough, I can always achieve 100% fidelity.
For local, yes. For local explanations, you can. For global, you are building a greedy decision tree, so you might not get to 100%.
Thanks. Yeah, there are a couple of other questions from the audience. I'll ask.
Sure.
I've been done. So there's there's one. This is algorithm called M5. It seems. So I've used M5, and it actually builds decision trees, and in the leaf nodes it fits a logistic regression. I think it's LR. So is this a similar approach, or is it different? That's the question. One of them.
Yeah, there are decision tree based explainability like low, FI, and so on. But this is more a linear model tree wherein even the splits are decided based on linear fits. So at the end, you will have linear fits at the leaf, but even the splits are decided based on it.
Was one other question in the chat.
Sure.
So it asks, is this in any way inspired from the TREPAN, TREPAN? It's a classic paper in 1995 published by Craven and Shavlik that showed how to extract tree-structured representation from trained neural networks.
I wouldn't say it's inspired, but one could think about it. If the audience is familiar with recent works from Cynthia Rudin, the idea is that why have an explanation at all? You could have just an interpretable model. In fact, the FICO challenge that I talked about was, so Cynthia Rudin's team told that you could just have an interpretable tree. So they got a prize for that. But yeah, if you can build a decision tree, extract a decision tree out of the complex model, that would be the ideal case. But with all the work being done on optimal decision trees and inferring optimal decision trees from the complex model, it's still not there yet in terms of the computational efficiency as well as achieving optimality. But that's a very good point.
So in essence, to build a simpler model, you don't actually need the full representation of the complex model. You just need essentially black box access to it.
Yes. So it is fairly, I mean, it is agnostic to what the model is. And so you can treat it as a black box.
I think that's all the questions that we have right now. Right. So there's one question asking whether the LME model, will it have high bias or high variance?
I'm not sure in terms of what the
Right.
bias or variance is in relation to. But I guess it will have all the properties that a decision tree, conventional decision tree models should have. Again, this is about explaining the complex model. It does not relate to the accuracy of the complex model. If the accuracy of the complex model is bad, it will still explain the bad model. So the ultimate objective here is to explain the complex model regardless of how bad or good the complex model is. So the bias and variance are.
I would guess that in this case, what it depends is, for example, if you don't have access to training data and you are generating your own training data, how much training points do you generate or how deep do you go in the tree? Those are questions that, I mean, in a practical sense, we need to answer, and those will actually affect the bias or variance rather than the method itself. Am I right?
Right, right. I mean, again, this is, I mean, when it comes to practicing this, it will be aid for a human modeler. It won't be a fully automated setup. So the modeler will have to choose these parameters, open parameters of the depth and so on. And based on that, and based on their business intuition, they will have to understand what the subpopulations within a leaf mean and whether to expand it further or not, and make deductions based on it. So it's more of an aid. And again, any explainability method cannot be a standalone. You will need to build an analytics pipeline around it to completely understand and solve what the model means and how the model is behaving.
Okay. Thanks, Nara. I think that's all the questions that we have right now. So if there are any other relevant questions in the Q&A panel, please feel free to answer them.
Sure. Thanks a lot, Harish. Thanks a lot. Thanks to the conference organizers. It was a real pleasure.